Can you see this fine?
Yeah, so
Maybe if Mal wants to make an introduction.
Okay.
So thank you everyone for joining us. It's my pleasure to introduce Andrzej Dragan. He's an assistant professor at the Warsaw University, right?
No, not anymore. I'm a professor for like a couple of years already. So
a professor, okay. Yeah, I got the information on your website, I guess. He is a visiting professor at the National University of Singapore. He is also an artist. You can see some of his art in his website, and also an excellent science communicator. You can see some videos from some years ago in his YouTube channel. They are quite nice. Today he'll be talking about quantum theory of tachyons. Without any further ado, I'll hand it over to you.
Thank you. So let me, you see my screen, right? I'm sharing it fine. Good.
Yes, but we don't see it full. Now it is full screen.
Yeah, okay. So let me see. So first of all, let me begin why tachyons make no sense whatsoever, because there are many reasons not to treat them seriously at all. In special relativity, it takes infinite energy to accelerate anything to the speed of light, not to mention beyond it. Lorentz transformations break down for velocities larger than c. They lead to imaginary numbers, which makes them unreasonable. So this is another reason why you should not take that seriously. There are, most importantly, problems with causality. You know that if you try to consider any signals that move faster than light, you immediately run into problems with causality, sorts of grandfather paradoxes where you are allowed for signaling backwards in time. So in principle, you could use those signals to kill your own grandfather, stuff like this. So causality is completely broken down. Now, some years ago, myself and Arthur Eckert wrote a paper where we addressed those problems. And we show that these arguments actually are unfounded. So, so far what I have mentioned can be debated. And the purpose of the paper was to show that, in fact, it is true that among those problems, there are problems with causality once you include faster than light particles in special relativity. But it turns out that those problems are not really self-inconsistencies or paradoxes, but in these causality is disturbed, but in a precisely way, the way that we already know from quantum theory. So you do have problems with causality, but as you know, in quantum theory, you can repeat the same experiments many times and you can get different outcomes, which shows that causality in quantum domain is not exactly the same as causality in classical domain. And well, you could argue that if you ask why a photon did one thing, not the other in particular experiment, you could say, oh, there is no reason, it's undeterministic. So what we argued is that this exact type of indeterminism arises naturally once you try to include tachyons in special relativity. And in fact, we turned the argument around and we said that if you begin with an idea that all inertial frames of reference are equal, including frames of reference that move faster than light, which was the original Galileo's idea because he knew nothing about speed of light. He postulated that all frames are equal. Only later we have found that, not all frames are equal. Some of them are more equal than the others because there is a limit of the speed of light. So we only allow frames of reference that move slower than light. But Galileo knew nothing about that. So if you just keep this original idea of all frames are equal, then what you get is some sort of indeterminism that arises naturally for free. You don't have to postulate it in quantum theory. Moreover, what you find is that also an idea that particles have to move along a single trajectory, unlike in quantum theory where particles can move along multiple trajectories at once, which we call superpositions, is also a natural consequence. So Arthur and I wrote this paper where we argue that, in fact, you can deduce a lot of most interesting parts of quantum theory from special relativity alone, but one that is not restricted to observers that move slower than light. So the argument, so what we have first shown is that if you ask a student to find all linear transformations that preserve the speed of light, then obviously this is a set of solutions that everybody knows, Lorentz transformations. But this is not the only solution. There is a second family of solutions that I show here. The second family is only well determined for velocities that are larger than c, and they satisfy all the requirements. In particular, they preserve the speed of light. So mathematically speaking, there are two families of observers, and they are both fine according to your postulates. So they preserve the speed of light. So if you want to discard the second family of solutions, you can do that, sure, but that will require an extra assumption. You will have to assume that second family of observers is unphysical. You have to discard it, and that's how you end up with normal special relativity. What we have chosen with Arthur is not to discard this second family of solution and see what will be the consequence. So technically speaking, the second family does not preserve the space-time interval. It changes the sign of the space-time interval. But if you're looking at zero intervals, which correspond to motions at the speed of light, then 0 equals to 0. So that means that what moves with the speed of light will also move the speed of light in the other frame of reference that move faster than light. It's a mathematical fact, so let me see what are the consequences. And we had some discussions about this with people, some writing comments. We had this ongoing debate. So let me show you the brief argument, the simplest possible argument to show how you do not really run into the serious problem with causality that I mentioned in the list, because the idea of Lorentz transformations breaking down for velocities larger than c is simply the fact that you are using the wrong formulas for this wrong case. You have two cases, and for each case you have to use different set of formulas. So what's wrong with causality? So the standard argument why you cannot signal faster than light goes like this. You have two guys, A and B, and they exchange a superluminal signal, and there always exists a frame of reference in which the order of these events, sending the signal and receiving the signal, is reversed. So you can always find a frame of reference in which the signal is first received and then sent at A. In that other frame of reference, it actually looks like it's B signaling to A. So the order is simply swapped. So let me now ask the following question. Suppose that we want to send a signal. What does it take to send a signal? You need to have two properties. First of all, you must have some carrier of the signal, a bullet, for example, that moves faster than light. And you must have a pistol that shoots those bullets. You can pull the trigger or not pull the trigger, depending on your choice. And that choice will determine whether you send the information or not. That's how you send bits of information, by making choices with your free will or whatever. Or there is some mechanism that you control. So that means if you want to send a signal, that there must be some chemical or physical or whatever process in the past of the event A. And that mechanism you have to be able to control to send signals. In the language of quantum theory, we would say there must be some local, hidden or visible theory of parameters that you can control. Now, on the other hand, if you send that signal to B, you simply shoot him with your bullet, and B is completely unaware of that fact before he is being shot by the bullet. So before the event B, there is nothing in the past of the event B that will determine the exact moment at which he is being hit by your bullet. And he's just surprised by being shot. And the same must take place in the other frame of reference. You change the frame of reference, and the mechanism still preserves, it's still present before A, but it's not present before B. Which brings you to a question: in that other frame of reference, what caused the emission of the tachyon at B? Where is the cause of that? What causes that event? One answer would be, the reason must be somewhere before A, on the other side of the whole story. But that is a non-local description, because you would say that the cause of B is somewhere far away at A, perhaps in the future. But if you are looking for a local explanation, is there a local reason for emission of that particle at B? You would say, no, there is no local reason. It looks completely spontaneous. And to an observer that looks locally at event B, that emission of the tachyon will look completely spontaneous and surprising. It's not going to have any local deterministic cause. So this is already interesting because you see that right away, by this simple argument, you see there is something indeterministic going on in this particular frame of reference, which is already quite interesting by itself, because in quantum theory, indeterminism falls out of the sky by, I mean, we don't know why things are indeterministic. We just postulate it because we have seen that in experiments. Here, it's a consequence of very simple Lorentz transformation. But then you can ask, okay, but in this frame of reference, in the second frame of reference, the event at B is spontaneous. In the first frame of reference, it's completely deterministic. What's wrong? You cannot have this together because that's clearly what's the word? It will clearly prefer one of the frame from the other. But if you want to insist that all frames of reference must be equal, and that is our postulate, in fact, we postulate that all frames are equal, and you see that in the second frame of reference situation is not deterministic, then by requiring that all frames are equal, we will have to say that this process of emission of a tachyon must be indeterministic in all frames in order for the theory to be covariant. And you see that the conclusion is that in principle, if you wanted superluminal particles to be present in special relativity, the price you have to pay for that is that they will have to be emitted spontaneously with no cause, with no local deterministic reason, which is very similar to what we know from quantum theory. When an atom emits a photon, for example, this is also an indeterministic process. So as a consequence of that, if you have particles that are being emitted completely spontaneously, you can't really argue how you use those particles to send signals. Because as I said before, to send a signal, you must be able to control the signal, but clearly it is not possible in this case. So your source will be emitting tachyons completely spontaneously, but since you cannot control it, you cannot send any physical information. And that's why you don't really run into any problems, because you would run into problems if you could send signals faster than light. And what I have argued here is that you won't be able to send signals even if you have a source of tachyons. At least it's not clear how to do it. And I show you some arguments, some discussions in literature about this argument. People try to argue how is it still possible, and as far as I understand, there is no easy way to send signals using tachyons. So even if tachyons existed, it is not absolutely clear how you would be able to use them to send signals. What is clear is that in any covariant frame-independent theory, existence of tachyons implies indeterminism of some sort. So that was one argument you made. So you could have, in fact, you could have tachyons in your theory, but the theory would not be deterministic. Another observation that we have made is the following one. Suppose that we are observing a photon or ray of light that moves from A, being reflected at the mirror at M, and then goes back to B. Then I'm going to say something rather obvious. If the light ray is actually a single photon, then if you measure the photon on the path from A to M, by detecting the photon, you will not be able to find the photon on the path from M to B. So if you place two detectors along the path of the photon between A and M, and the second detector between M and B, only one of those detectors can click. Either first detector clicks and then the second one will not, or the other way around. It's quite obvious. Now, let me look at the same situation, but from the frame of reference that moves infinitely fast. I already have formulas for that, because that is formulas that I derived that allow for motions faster than light. In fact, those formulas correspond to hyperbolic rotation of spacetime, only the angle of rotation is not bounded from above by 45 degrees. You can now have the hyperbolic rotation going past that, and in the limiting case of velocity going to infinity, you can actually check that the transformation boils down to simply replacing time and space. It's a hyperbolic rotation by the angle of 90 degrees. Which means that this whole situation that I described is going to look like if you just replaced axis of time and space, and the observer that moves infinitely fast call space what we call time, and vice versa. In that frame of reference, the whole scenario I described looks like this. There's an M, a point where a pair of particles emitted, one to the left, one to the right. So in this frame of reference, the number of particles seems to be different. Now you have two photons, not one. However, if you try to measure those photons and place two detectors on two different paths, as I argued before, only one of those detectors can click, either the first one or the second one. It's not clear which one, but clearly you cannot have two clicks at the same time, because the physical outcomes of experiments cannot change based on which frame of reference you are using to describe it. So we have argued that as a consequence, what arises is a situation where a photon seems to be described by two paths at the same time, as long as you don't make measurements. But once you make a measurement, you will always find the photon either on one path or the other, but you will not find the photon at both paths at the same time. And then we generalize the same argument to multiple paths. We also shown that in order to characterize those paths using frame-independent invariants, that has to involve some sort of superposition where each path is attributed a complex number. You have to add complex numbers. There's this mathematical argument I'm not going to go into. Anyway, the claim of the whole thing is that if you really treat seriously both families of mathematically allowed solutions, and you argue mathematics says that you can, in principle, tolerate all the axioms of special relativity and get two possible solutions. If you treat them seriously, what you get for free is indeterminism. You get for free a situation where particles have to move along multiple paths at the same time in certain scenarios. And what you also get for free is some sort of quantum mechanical description where you have to superpose probability amplitudes, which are complex numbers, and we argue that the simplest possible expression that makes sense covariantly involves modulus square of sum of all the probability amplitudes. So the conclusion of that was that quantum theory is in its roots something very relativistic. That's the reason why quantum theory actually is the way it is, has to do with relativity. And only because there are two families of solutions that have to be treated seriously, you actually get indeterminism, superposition, and so on and so forth. So that was the first observation. What about energies and momenta? We argue about that as well. So if you just proceed with standard derivations of expressions for energy and momentum of your particle, you can actually complete all the special relativistic expressions for that second case of particles moving faster than light, and then you find that the energy, covariant energy expression for energy and momentum involves the following expressions, where the denominator has this reversed factor where v squared over c squared minus 1 is instead of 1 minus v squared over c squared. And these expressions are quite interesting because they show that tachyons, if they existed, would be characterized by energies such that the faster it moves, the smaller the energy it has. So in fact, if you wanted to slow down tachyon, it takes energy, and if you wanted to slow down the tachyon to the speed of light, it will take infinite energy, which shows that in fact it is not possible to cross the speed of light. Either for normal matter you cannot accelerate it faster than light, or you could also not be able to slow down tachyons below the speed of light because that will take infinite energy. But in principle, the theory allows for tachyons to exist always moving faster than light. And that results in conclusion that, well, in terms of quantum theory, the conclusion is that energy, as if you study these expressions, does not have to be always positive, because even if you have positive energy, it can be also covariantly changed into negative energy by changing the frame of reference, which means that it is inevitable to use negative energies in your theory. And if the theory is to be covariant, an idea of negative energies must be somehow adopted to the theory. This is one of the consequences. zero energy particles move infinitely fast, but you can also covariantly change that motion to motion backwards in time, which corresponds to negative energies. So the difference with normal particles is that normal particles in quantum theory can either be matter or antimatter, which corresponds, mathematically speaking, at least according to Feynman's interpretation, to particles moving either forwards in time or backwards in time. And if you have an electron, it's going to be an electron in all frames of reference. It's not going to change into antiparticle because you simply started to move. The same for positron. Positron is always a negative particle energy, no matter how fast you move. With tachyons, it's different. With tachyons is that you can change a tachyon into antitachyon by simply changing the frame of reference. So that is the qualitative difference with normal particles. The question whether those tachyons exist or not is a different story. I'm going to address it later. But what I'm saying so far is that in principle, the framework of special relativity allows for those particles. And mathematically speaking, at least, they should be well defined. The only question is, what are the physical consequences? And as we have tried to argue, the price you pay for their existence would not be that high, because what you get is really retrieve what we already know from quantum theory. Are there any questions at this point about this?
So I guess you got to the notion of superposition in these frames with infinite velocity, right?
Right.
So how should I understand this? Like, what's the message about like experiments in which we can verify superpositions?
So one observation is that if you have a superposition in one frame of reference, that could be in other frame of reference a motion along a single path. So a superposition can be a result of Lorentz transforming a normal motion along a single path. But most importantly is that if you insist on the Galilean principle that all frames are equal, no matter what the speed of light, what the velocity of your motion is, then you will not be able to avoid superpositions. They are necessary, right? So in a way, superposition principle is a necessity for special relativity treated as a whole thing containing both counterparts. So if you normally have the normal structure, how you teach students this is this. You derive special relativity, then if you are careful, you will see that there are two solutions. You will say, oh, we reject the other solution. And then you have a classical theory that we know from regular lectures. And then on top of that, you have to postulate everything in quantum theory, right? You have to postulate that the word is not classical. You have to introduce indeterminism. You have to introduce superpositions. You have to postulate all that. What we propose is that instead of doing all this, you just assume all frames are equal. And then you don't have to do much more. You just see what are the consequences. And many of those quantum mechanical postulates just are natural consequence. You don't have to postulate them. So there is nothing really dodgy or surprising happening here, other than realization that quantum effects are just consequences of relativity.
I have one question. This indeterminism, it appears when I change from the reference frame of tachyons to the under subluminal reference frame, right?
No, not really. Not really. So not really, because here in this discussion, I only used frames of reference that move slower than light. I had a tachyon, and I observed the tachyon from two subluminal frames of reference. And already here you have indeterminism. I don't want to go into details, but you can use similar arguments to show that normal particles also have to move, also have to behave indeterministically. So this also applies to normal particles. But I didn't want to focus on this aspect of this. But the message is that if you have all types of particles, including faster than light, and all types of observers, including faster than light, indeterminism is inevitable.
And if you would be just on the tachyons frames,
right?
Would you also find indeterminism comparing the tachyons, or no? You should compare with the subluminal.
There is an argument to be made that all particles will behave indeterministically in all frames. What you can also say, which I did not yet, is that in this simplified case of 1 plus 1 dimensional spacetime, where you only have one time and one space, which I have shown focus 1 so far, there is no difference really, and you could be a tachyon yourself and you wouldn't know about this, because from the point of view of a faster than light frame of reference, we are tachyons, right?
Okay.
And they are the other way around. So there is a perfect symmetry here. That symmetry is, by the way, broken in real space-time that has 3 spatial dimensions, and this is what we discussed later. So I'm going to come to this now.
Okay, thank you very much.
So again, going back to our arguments, it's not true that it takes infinite energy to accelerate anything. I mean, it is true, but it's not a counter argument, because you have other types of expressions for energy momentum for your tachyon that moves faster than light. Lorentz transformations do not break down for V larger than C, because simply there is a second set of solutions that you have to use for that case. And problems of causality, I mean, causality is not preserved in the classical sense, but you cannot call it a problem. It's actually bringing you to what you know from quantum theory. So it's actually a confirmation, not a problem. So these arguments are not so decisive, but there are other arguments. For example, people argue that in 1 plus 1 dimensional spacetime, it could make sense, but in 3 plus 1 dimensional spacetime, it is not possible to generalize these concepts, because the symmetry group that you obtain this way is too large. People have shown that if you consider 4-dimensional generalization of Lorentz transformations, and you want to base a symmetry group based on that, that group will be too large. For technical people, the symmetry group that contains faster than light transformations is going to be SL4R, which is the special group containing all linear transformations, which clearly is too large to be a symmetry group, because it contains operations that are clearly not symmetries, like stretching space or direction-dependent time dilation. It's physically impossible to make this a symmetry group. So people argued, okay, it makes no sense in 4-dimensional spacetime. So we wrote another paper on this, where we generalized the idea to 4 dimensions, and we explicitly show how to construct the theory in 4-dimensional spacetime, and how to address the problem that was mentioned before of the symmetry group that is too large. Just before I proceed, let me tell you what is the solution. The solution is that although in 2-dimensional spacetime there is a symmetry between frames moving slower than light and faster than light, that symmetry is not present anymore in 4 dimensions. What you can do, the best you can do, is to have a situation where you have 2 families of observers, one family moving slower than light, and one family moving faster than light, but those 2 families are not exactly the same. So among all inertial observers moving slower than light, there is a symmetry, they are all equal. Among all the observers moving faster than light, there is also symmetry, so they are all equal. They have the same laws of physics, but there is this difference between observers moving slower than light and faster than light. So there is a way to discriminate whether we are tachyons or not, in absolute sense. So the symmetry is broken. That's why going to a frame that moves faster than light is a legal operation, but it is not a symmetry. It will change the laws of physics. And then actually we gave a specific example of how Maxwell's equations would look like in the frame of reference that move faster than light, and they are going to be different equations. So an idea introduced by Galileo that all frames are equal has to be made weaker, because indeed it is not probably possible to have that rule holding in 4-dimensional space. But other than that, it is possible to formulate a theory in both subluminal and superluminal frames of reference, with the restriction that they are not exactly the same. Which actually is nothing wrong, and there is nothing wrong with that. For example, if you think about Rindler frames of reference, ones that move with acceleration, they are also different from inertial frames of reference, right? They are physically different, but they are still a valid point of view, right? You can introduce uniformly accelerated frame of reference and describe your chosen theory in that frame. It still makes sense. although the laws of physics in this non-inertial frame of reference are going to be slightly different. And it's the same with tachyons. In tachyonic frames of reference, there are two families, and the second family of solutions, you can call them inertial observers that move faster than light, but you will have different laws of physics in those frames. And I would like now to explain exactly why this happens and what is the situation. And again, it gets even weirder than what I said before, so you have to be prepared that weirdness of that is even exceeding what I have been talking about so far. Again, our goal is to simply explore how to construct such a theory and what are the price we have to pay. So let me now explain what is the situation. So let me begin by showing you these formulas that you already see. These are Lorentz transformations in 4 dimensions, regular formulas that you know, but written in a way that they are valid for any direction of velocity. Velocity v is a vector, can be directed anywhere. This is just Lorentz transformations between two inertial observers in any direction of velocity, given that those two frames are unrotated relative to each other. So there is no Wigner rotation between them. These expressions preserve space-time interval. So they are, what it means is that if you write an expression without primes and you transform the expression, you get the same expression with primes. Now, in order to derive this formula, you start with one-dimensional transformations, you add transformations for y and z, trivial transformations that do nothing, and then you just get these formulas. If you do the same thing, exactly the same thing with the second family of solutions faster than light, you get these expressions, which also are valid only for velocities larger than c. But there is a fundamental and qualitative difference here. So if you notice that I'm using bold-face fonts to describe vectors and thin quantities, thin letters to describe scalars or one-dimensional quantities, T and R are normally considered T to be one-dimensional, R to be three-dimensional, while the prime quantities are written in the opposite way. So you have one-dimensional space and three-dimensional time. The reason for this is the following. It's a way of writing formulas in a compact way. So let me first not go into interpretation of this fact, but mathematically speaking, in both frames of reference, you have 4 coordinates to characterize any space-time event. In frame of reference moving slower than light, it's time and three-dimensional space. We are using in superluminal frame of reference other parameterization where you have one-dimensional position and three-dimensional time. Why do we do this? Well, the reason is this. If you limit yourself to two-dimensional space-times, as I argued, the transformation flips time and space. So it changes the sign of the space-time interval, and y and z components are not going to be changed. So by doing this operation, you notice that the sign of y prime and z prime is now not the same with the sign of x prime, but it's the same with t prime. So in the expression for the space-time interval, the sign of the individual components group together such that the negative sign in front of time is the same as negative sign in front of perpendicular directions in space. So it is natural to group them together. If you do that, this is the set of formulas you obtain. And now it's a matter of interpretation. What does it mean? And in special relativity, normally you would argue that the only difference between time and space is the sign in the space-time interval. Other than that, they are just coordinates characterizing events in space-time, and the only physical mathematical difference is the sign, the minus sign. If you adopt this interpretation that what defines time and what defines space is a sign in the space-time interval, then as a consequence of this principle, you would have to conclude that in a frame of reference that moves faster than light, you will have 3 time coordinates, 1 space coordinate, which makes it different from regular frames of reference that we know, where you have one-dimensional time and three-dimensional space. And So that's the reason why there is this discrepancy and the difference between frames of reference, and then you cannot say anymore that all frames are equal. Physically, it's going to be completely different. The question is, does it make any physical sense, and how to make any sense out of a situation where you could move faster than light and then go to a universe where there are three-dimensional time. So the purpose of the paper in classical quantum gravity is exactly to explore this idea, and I will spare the details. Anyway, it takes really some effort to even talk about the simplest questions like what is kinematics, what is velocity, how do you define velocity. We go through all that and eventually derive the covariant definition of velocities in these crazy situations. What is interesting is that we find that once we are done with all this, we find that if you define the velocity in the right way, the rule that light always moves with the speed of light is still preserved. So if you have a photon moving with the speed of light relative to our frame of reference, in the faster than light frame of reference that has all this crazy kinematics and all the crazy definition of velocities, the speed of the photon is still c, is still preserved. Which is quite interesting, because then again, if you ask your student to derive all linear transformations that preserve the speed of light in four-dimensional spacetime, then Lorentz transformation is only one solution. The second solution is still possible for velocities faster than light, and they will still preserve the speed of light, which we have verified explicitly. So this is still satisfied. So this argument really is still not valid. It is in principle possible to have frame of reference moving faster than light in four-dimensional spacetime. The story is even crazier than what I have started with. It's not for me to decide whether it makes physical sense or is just a mathematical artifact. It's really hard to say. But in principle, the whole structure is there, and mathematically speaking, this is not as crazily wrong as it seems at first. Okay, any questions or comments at this stage?
I have a quick question. So Magda here.
Hi, Magda.
Cześć, Andrzej. I mean, you mentioned the kinematics so far. So can you comment what happens with the notion of? I mean, it seems for momentum would acquire similar sort of feature that you will have three energies.
That's right.
And momentum. So is there anything interesting from that perspective?
It's all crazy interesting. So
more?
if you spend like a semester learning special relativity in a normal way, then you can spend another semester exploring what are the consequences that involve this. In particular, all three-dimensional quantities turn into one-dimensional quantities and vice versa. So if you try, for example, to write Maxwell's equations, I mentioned before, where you have four currents and one-dimensional density of charge, this is going to be the opposite in the other frame of reference. And you can write equations, Maxwell's equations, that look quite similar, but with vectors being put in wrong places, right? So you have a vector of charge density and one-dimensional charge current density, and so on and so forth. So this is the price you pay. I mean, you have to be careful about the vectors. But in principle, technically speaking, it's possible. We do not want to be decisive whether this is just a mathematical trick or something more fundamental. I tend to sympathize with Dirac when he first, famously when he tried to write the Dirac equations. That equation also had two types of solutions for matter and antimatter, and all sane persons in the room would say, oh, you have to discard the second solutions are unphysical.
Mm-hmm.
His brave choice was to say, no, mathematical equations smarter than myself. If the equation says there are two solutions, then so be it. I mean, we could try to follow the same logic where we say, yeah, I mean, if you postulate that all frames are equal, or transformation has to be linear to be mathematically more specific, and speed of light has to be preserved, then Lorentz transformation is just half of the answer, right? There is a second half
Yep.
that has to be explored.
Sure. Cool. Okay, I'll let you continue and
There's a question
Yeah.
because this is the classical part. I want to come to quantum part next.
yeah, perfect.
Hi, I don't know if I can ask a question now.
Yeah.
Yeah, right. So I want to comment. First of all, a quick question to be sure that I understood correctly. So when you do the faster than light transformation, you actually switch t with just one of the spatial coordinates. So for example, t with, let's say, x, if you do the...
That's right.
All right. But now is my consideration, because so if you want something similar already happens in the Schwarzschild metric. And I know this is general relativity.
Yeah.
But my point is different, because when you are outside of the horizon, you can use t as a time coordinate. And
That's right.
But if you're inside the horizon, then you switch t. So t
Right.
is a spatial coordinate and r is a time coordinate.
Exactly.
But my question is now, because now you say if equations tell you something, you have to trust them, basically. But my point is that Schwarzschild metric tells you something which is wrong, which is that there is a singularity at r equals to m. And this is what's happening here is something which happens basically in a metric which has wrong coordinates.
Yeah. This
So
is
my
something
ask-
that yeah. So this is something we are talking about a lot, and you know very well that you can, when you describe Schwarzschild metric, you can go to Kruskal coordinates,
Yes, exactly.
and then everything is smooth
Yes.
on the horizon, and the solutions that were wrong just 5 minutes ago are not wrong anymore once you write them in other coordinates, right? Which shows that the solutions were right, which is obvious when you use the Kruskal coordinates. And since the correctness or incorrectness of solutions cannot depend on the choice of coordinates, that brings you to the conclusion that those solutions have also to be right in the case of Schwarzschild coordinates. So
Yes,
what
but the
to make of
interpretation
it?
changes though.
Yes, but the
Because now-
interpretation is very difficult. So
Yeah.
if you adopt this vision that we propose, the interpretation of the problems in Schwarzschild coordinates is the following. Schwarzschild coordinates are meant to describe a black hole with respect to stationary observers that do not move relative to singularity, right? They do not move relative to the black hole, where the black hole is static. It is only possible to do so above the event horizon, because under the event horizon, you will not be able to have stationary observers. They will have to fall into singularity. Unless you allow for faster than light observers, because those can be stationary inside of the black hole, will not move. And in fact, what happens is exactly that. The solution of the Schwarzschild metric inside of the black hole correspond to observers that are tachyonic observers, but they are at rest relative to the singularity. And that's why time and space is reversed, simply because that corresponds to the description of the black hole from the point of view of the observers that move faster than light. So our conclusion, just let me say what is the point of view that we kind of favor, is that you are able to discard faster than light solutions from special relativity, but then you'll be haunted in the case of general relativity, where you have to deal with this problem. And people normally would say, oh, this is unphysical, or it's, I don't know, it's wrong interpretation, or just fake wrong coordinate system. We don't think there is a wrong coordinate system. A coordinate system doesn't matter. I mean, you can trace any coordinates you want. So we believe that the only way to interpret those solutions without saying that these are wrong coordinates is by introducing observers that move faster than light. So you can get rid of the problem in special relativity, but it will go back in general relativity.
All right, I would have many things to say, but I guess it's just first finish the talk. And then
Yeah. Right.
I don't know if I will be at the end here, but anyway.
So this I wanted to make this brief just to summarize what was happening before on the level of classical theory, because now I want to go to quantum theory, and there are more problems in quantum theory. First of all, I said that we have to deal with negative energies. They are inevitable already in the classical level, and you know that in quantum field theory you cannot have negative energies because you won't be able to formulate the theory. Lagrangian needs, or Hamiltonian needs, positive energies. Also, people try to have tachyons in quantum theory, and there is a problem with stable and frame-independent vacuum. People have shown that it's not possible to have a stable, independent vacuum frame-independent vacuum in quantum theory, quantum field theory. Other thing that is terrible in that is that once you try to introduce annihilation creation operators, the annihilation of the commutation relations are not going to be covariant. And Aharonov tried to fix this, Sudarshan tried to fix this, Feinberg, another tried to fix this, and they all failed because these non-covariant commutation relations were still a problem. Then you have other problems when you try to do perturbation theory. You have problems with loop corrections, some technicalities, and possibly other problems that I don't even know of. So to address those questions, we wrote this other paper. This is the reason for me to give a talk today that solves 3 of those problems. So we showed that you can avoid problems with negative energies, you can avoid problems with frame-dependent and unstable vacuum, and you can avoid problems with non-covariant commutation relations. So it is possible to quantize the theory on the basic level. So this is what we have solved. What we have not solved is higher order theory that includes interactions. And there are some serious problems we don't know how to solve at the moment, and so I'm not going to discuss this. But first of all, so this is the paper we wrote, PRD, where we actually show that these major obstacles can be removed. But the motivation for the whole thing, why to even bother, right? Okay, fine, it's mathematically possible, by why should we bother? We know tachyons do not exist, right? They are not physical. Maybe mathematically they will be possible, but in actual reality they don't exist. This is not entirely true, and that's the motivation that drives us in this project forward. Is something that you can find in any textbook on quantum field theory when you want to characterize Higgs mechanism. So this is a page from my favorite textbook, Średnicki's, on quantum field theory, and you always have this situation where you have to consider negative square mass potential to describe Higgs mechanism. Now, technically speaking, tachyon is a particle that is characterized by a field that has negative square mass. Simply because if you write an expression between energy and momentum for normal particles, it goes like E squared equals P squared plus M squared. For tachyons, E and P is inversed, which corresponds to the situation that E squared is equal to P squared minus M squared. So another name for tachyons in quantum field theory would be a particle with negative square mass. And apparently you have to use particles of negative square mass to characterize Higgs mechanism. This is the exact expression I was talking about. And then people hand wave, okay, but you have to use this, but then it's, after all the operations, you can discard that fact and forget about that, which is true. However, there is no Higgs mechanism without that part where you have to talk about for a moment with about particles with negative square mass. And we believe that there is something more to it than just a mathematical trick. And in fact, in order to characterize the whole process of spontaneous symmetry breaking with Higgs mechanism carefully, you will have to deal with tachyons at some point, and you have to address the question how to characterize them using quantum theory. So to be more specific, this is the picture you normally get in quantum field theory for a Higgs mechanism, and you would say that the Higgs potential that characterizes the theory has this funny shape of a Mexican hat. I don't know if this is still cultural appropriation, not for me to decide, but that's how they call it. Anyway, in the current day scenario, nowadays, in the universe, Higgs field is lying somewhere in the middle of this row around the hat, outside of the maximum, in a local minimum, where this local minimum introduces the situation where mass of the Higgs field is indeed normal. It's a positive square mass particle. So Higgs particles are just normal particles as we know them, moving slower than light. And whenever you have a potential that has a minimum, that's the situation. Your particles will have normal mass. They will move slower than light. If you had tachyons, on the other hand, the quantum potential of the tachyon will be the inverse parabola, where there's a maximum. That will be tachyons. For Higgs particles, as you can see from this picture, it can be sometimes the minimum, sometimes the maximum, depending on the configuration of the field, the state of the field that you are starting with. So in principle, if that picture is correct, that standard picture characterizing Higgs mechanism, it should be possible to put a field in such configuration that it's on top of the potential, where, technically speaking, excitation of the field are tachyons. So if somehow we would be able to engineer the Higgs field to make it go to the top of the potential, the hypothesis is that those particles will behave like tachyons. So, make it short, Higgs particles would move faster than light, as long as they sit on the potential, on the top of the potential. Once they collapse to violating the symmetry and end up in the local minimum, they become well behaved and they become normal particles, which is the situation we know from experiments nowadays. But if somehow for large energies you could make the field go to the top of the potential, the claim is that that particle should have properties of tachyons. And that's why it's actually reasonable and valid and important to try to describe this situation using quantum mechanical language, because, which is quite surprising, there is no good theory, fully quantum theory, characterizing the transition from the top to the bottom. What we currently have are semi-classical, where you have a classical hand-waving arguments mentioning that the field is classical and then somehow collapses to the bottom, and then we contest the theory. But there is no fully quantum mechanical mechanism that characterizes all. And I'm running out of time, as I can see. So I will just briefly tell you how we propose to solve this problem, how to quantize the theory. I will probably skip some technical details, unfortunately, and I will just focus on this simple diagram, because it's essentially it captures the whole idea. Suppose that we already have quantum theory of tachyons and quantum theory of normal particles, and you have some sort of interactions that are described by diagrams like this, Feynman diagrams, where, for example, on the left-hand side, you have a situation where a normal particle emits a tachyon, and then it's scattered to some other state. Then from special relativity, we know that there exists a frame of reference in which the tachyon goes backwards in time. It is inevitable, it's just kinematical law. You will have to deal with the situation. And also, that situation involves not only tachyon moving backwards in time, but also having negative energy, which is a problem. And that's the whole source of problems in quantum theory, which does not allow negative energies. Energies must be positive. So what is the solution? Well, you can see that you can always reinterpret this second picture. But so instead of saying you have negative tachyon, so you have anti-tachyon going backwards, you have negative energy tachyon going backwards in time, you can say, no, it's a positive energy anti-tachyon going forward in time. So you can always reinterpret this second diagram and say that the particle has changed into antiparticle by Lorentz transforming the process, which can be covariant. But notice there is a problem, because in normal quantum theory, the assumption that you have to take for the theory to make sense is that you cannot change the number of particles by just moving. If I'm observing a situation there's 0 particles, if I move, there must be 0 particles. If I had 5 photons in one frame of reference, I will have to have 5 photons in another frame of reference. You cannot change the number of particles by just moving. Lorentz transformation does not change the number of particle operator, which is the primary assumption for the covariant formulation of second quantized fields. And that's the problem here, because you see that by moving, you begin with a situation where there was 0 tachyons at the beginning and 1 tachyon in the output state. But when you move, it's the opposite. You have 1 tachyon in the input and 0 tachyons in the output. So you change the number of particles in the input state and in the output state, Hilbert space. And that's the source of all the problems. The way to fix it is to say, well, instead of considering input states and output states separately, you have to consider the whole thing. You have to consider the space of all input and output states together, which has a mathematical structure of the tensor product of the input states and output states. And then if you treat this together as a as the boundary conditions of your considerations, where you consider both past infinity and future infinity states together, then you can get rid of all the problems. And I will unfortunately have to skip all the mathematical details, but essentially we argue that you can introduce frame-independent vacuum state. You can have you can avoid problems with negative energies by reinterpreting negative energies in terms of antiparticles. We show that commutation relations are covariant, and the whole theory is actually covariant, provided that the Hilbert space you consider is this doubled space where you have joint description of input and output state together. I will have to skip all the details. What I will mention is that we call this twin space, and apparently you can make the whole thing to covariant, but the price you pay now is this. In classical theory, in non-quantum classical theory, you can always predict the future based on the past. That's standard determinism. You have it in Newton theory, you have in electrodynamics, you can predict the future. In quantum theory, you cannot predict the future given the past, but you can predict probability of the future given the past. So you can compute probabilities given the situation in the past Cauchy surface, and those probabilities are well defined. If you want to include tachyons, this is no longer possible. And in order for the theory to predict what's happening now, the probability of what's happening now, you not only have to introduce, define what happens in the past, but also what happens in the future. So the Cauchy surface problem, the boundary condition problem, is somehow modified, where in order to say what the probability of what's happening now is given by joint information from the past and from the future. And that sounds already crazy enough. However, it's a very old idea that we have discovered. I mean, probably you have heard of Aharonov's two-state vector formalism, which is exactly that, which had a completely different motivation. The motivation of Aharonov from the 60s was to construct a quantum theory that is time-symmetric, and he has shown that in order to have a time-symmetric quantum theory where measurement outcomes are time-symmetric, you have to extend the Hilbert space and say that probabilities of outcomes must depend on the past and future together in a symmetric fashion. And he actually constructed the whole theory. It's called the two-state vector formalism, and it was treated as a nonchalant, extravagant interpretation of quantum mechanics that was completely indistinguishable from the normal theory. What we have found is that this crazy interpretation is in fact necessary for the theory to be covariant when you want to include tachyons. And we are currently trying to push this forward and try to understand to what degree you can construct quantum field theory using some relativistic version of two-state vector formalism, because we see already that this is a way to make the theory covariant. And at least 3 of the major problems with construction of the theory can be resolved by just extending Hilbert space and treating future and past in a symmetric fashion, which turns out actually to be not only necessary for our approach, but it turns out to be necessary in loop quantum gravity and other at first unrelated fields. So this seems to be like a necessary point in many unusual, unorthodox approaches to relativity and quantum theory combined. Sorry, I'll have to skip all the details, but if there's time for discussion, I'll be happy to discuss them further. Okay, thank you.
Thank you. Any further questions?
I have a question, if I can. Sure. So one
you muted yourself. Sorry, Andrea, you muted.
Andrea, you muted yourself.
Yes, 1 second.
You are still muted. We cannot hear you. So.
Yeah, I think he's just asking someone to.
Okay.
Yeah, sorry, I needed a couple of seconds. My question has to do with the fact that you were saying about the mass that you get m square negatives in order to do the Higgs, and then you were arguing about tachyon presence. Basically, you said that in order to treat the Higgs, you need the tachyons at some point, if that's what I understood. But the mass that you have in the Lagrange, so tachyons are, as far as I understand, are particles which are on shell with imaginary mass. But the m squared that you have in the Lagrangian for the Higgs is not an on-shell mass. That's just a parameter, because you define on-shell masses via the divergence of the propagator, and then. So my question is, how can you say that there are tachyons if tachyons are on shell with imaginary mass? I'm saying about the treatment of the Higgs. So tachyons are on shell with imaginary mass, but the mass that you have to assume that is negative, m squared negative for the Higgs treatment is not an on-shell mass. So this is my question.
So let me start just briefly say what the statement is. First of all, normal particles have positive square mass on shell. If tachyons existed, they would correspond to particles with negative square mass on shell. Right? So their shell is different, right? So they have a shell such that negative mass is involved. The potential for the Higgs particle is such that it's sometimes positive square mass, sometimes negative square mass, depending on the situation where you're sitting in the potential. So if you are dwelling in the minimum of the potential, the on-shell mass is positive square mass. If somehow you could take the Higgs field and put it in the state that it's sitting on top, then the on-shell mass in the approximation around the initial point is going to be negative square mass. So the shell has a different quality. Now, the standard, what textbooks say is exactly what you say. It's just a parameter. It should not be treated as real mass. Sure, it's just a name how you call things. But if you define mass as exactly the parameter in front of the phi square terms in the Lagrangian, then according to that definition, the on-shell expression for tachyon is negative square mass, and that's exactly what you have for Higgs field at the 0 phi configuration.
Yeah, so you're using you're basically using a different definition of mass, which, however, is
yeah.
So basically, so you measure the Higgs mass, and the Higgs mass is whatever number, positive number.
I'm not going to insist on what you should call mass, what you should not call mass. What I'm saying is that if tachyons existed, their shell will have a negative square mass. Right?
Yes,
right? So if you call this real mass or maybe some other parameter, I don't care. I mean, this is just a definition, so it doesn't really matter physically.
Almost, because then the parameters in front of the Lagrange are susceptible of is English counter terms, so you can renormalize them. You have. I mean, it's not as if you pick the parameter and then that's it, you're happy, because it doesn't work even if in electrodynamics or whatever.
You're absolutely right. So if you try to have interacting theory, it is possible to have that interacting theory within first order perturbation on the tree-level diagrams. Once you have loop corrections, once you do normalizations, you run into problems that we don't know how to solve. And actually, the physical reason I think we understood what is the physical core reason why there are problems with interacting theory. And they still boil down to very simple special relativistic argument. And the argument goes like this. If you have just normal particles with positive square mass, they can scatter from themselves, they can emit themselves, they can decay into other particles. But for example, if muon decays into an electron and neutrinos, it is possible, but the mass of all particles must change. For example, it is not possible to emit a particle without changing your mass. It's kinematically impossible. That's why an electron cannot absorb a photon. Right? It has to change the mass, which goes into interactions with other particles. So atom can absorb free electron cannot absorb a photon or emit a photon. With tachyons, it's different. With tachyons, actually, it's kinematically possible to emit a tachyon and just change your velocity. So if you look at expressions for energy momentum, it is kinematically possible to emit a tachyon and just move with different velocity without changing the mass. So an electron could emit a tachyon and still be an electron. And this can happen many times. So an electron can, in principle, emit infinitely many tachyons in different directions, and that will be in agreement, in accordance with conservation of energy momentum. So the problem is that if you look at asymptotical path, asymptotical future, and I have a process of interacting fields, normal field interacting with tectonic fields, during this infinite time, you'll have infinite many emissions or absorptions. So the final state or the input state must contain infinitely many particles. And it goes beyond normal treatment where you have input state that has certain state of, in the Fock space, certain number of particles, certain number of particles in the output, and you can just compute probability amplitude for the process. With tachyons, it's going to be more tricky than that because you have to deal with these infinities, and I don't know how. And we don't know how. Mathematically, that manifests in the fact that when you compute loop corrections, you get imaginary terms that should not be there, which was pointed out by a colleague of ours from Korea who made the calculations and pointed this out. So it's a technical problem. Maybe it's a fundamental problem, we don't know, but indeed there are problems that we cannot solve at the moment with interactions and higher order correction.
Yes, and also if I can point something out, because usually we use Hermitian Lagrangian. So for tachyons, there shouldn't be, counterterms can only be real because you cannot have imaginary coefficient in Hermitian Lagrangian basically. If you have real,
if the fields if the output states are stable, and they are not.
Yeah, right. Yeah, there are so many things to discuss, but thank you for the answer.
Anyway, the optical theorem is capturing all these problems already.
Yes.
Any other questions? Well, so I'll just ask out of curiosity, because you have the connection with the two-state vectors formalism, and I want to ask you to see if you have any connections with weak values, if anything appeared already in your analysis.
We don't know about that. I know there are problems with weak values. I know that Aharonov and others try to push hard to find any verifiable observational evidence that the two-state vector formalism makes any sense. And I know that weak values have been criticized as unphysical. They have some crazy properties we don't know. So we are not really looking into this. We don't even know whether it makes sense or not. In fact, the only reason why we are looking in the two-state vector formalism is that we are forced to, due to the covariance condition. So although in normal non-relativistic quantum mechanics, two-state vector formalism is this abstract, funny interpretation that nobody cares about, except for Aharonov and a bunch of people who are working on this. Well, I don't want to be rude or brutal, but it's like a very side quest that many people pay attention to. We kind of realize that this is absolutely necessary. We just cannot have a covariant theory without that. So that's why we are forced to look into this. And seems to be really interesting and very, you don't understand more than just basics, but there are some very interesting implications of using two-state vector formalism in quantum field theory, including possible scenarios where evolution does not have to be necessarily unitary in some circumstances. Very interesting consequences to explore, but we are just beginning, so we don't understand more.
Yeah, I was asking because, in some preparing measure scenarios, anomalous weak values can be like proof of contextuality, so they can also be used to characterize some quantumness about the system. So I don't know, maybe there could be something there.
I'm not an expert. I know that there's big argument going about this. People kind of argue back and forth. We actually tried to publish some papers in two-state vector formalism because we wanted to understand some basics, and we had to fight with referees with counterproductive comments because they don't agree with each other. So I know there is a big debate going on in this field. We stepped into it, and now I'm kind of sorry about this. But yeah, I know there's a problem with weak values. I don't know the solution or don't have much to say about this, unfortunately.
Thank you. Other questions?
So if I was just to quickly summarize this mess that I presented today, it's not, I mean, whether tachyons exist or not, it's one thing. Whether they are logically allowed in physics is a different thing. And what I try to argue is that it's not absolutely obvious, at least, why they are not allowed. The standard arguments don't make much sense. So maybe there's an argument why tachyons make no sense. Maybe it stems from quantum field theory, but it's certainly not something really basic as to say the grandfather paradox or energies explode or stuff like this. These arguments are too quick, so you have to be more careful to formulate them. Anyway, I think there's some interesting structures to be explored, and we believe a relation between quantum theory and relativity, the connections between those theories go much deeper than people thought so far. Well, we know of Bell's inequalities that show that in quantum theory you cannot signal faster than light, or at least if you don't signal faster than light, your theory can be deterministic and local. So somehow already in non-relativistic quantum theory you have a role of speed of light appearing out of nowhere. So, and in a way, we know that there is no problem with relativity versus quantum theory simply because of the indeterminism, right? If theory was deterministic, you could send signals faster than light, and because theory is not deterministic, there is no problem with relativity. So this is not a coincidence. We argue that the reason for that is that it's not coincidence because quantum theory is a result of relativity, and it stems from relativity, and not relativity naively understood as this half of relativity, but actually extended to the full structure involving all frames of reference. So that's why you have these coincidences in non-relativistic quantum mechanics where you do not have problems with relativity. It's still the structure seems to be much more difficult than can be tackled easily. So we struggle with understanding at the moment interacting quantum field theory, and we don't know whether the solution exists even, or whether it exists in a form that is similar to the standard approach to quantum field theory. But the motivation for that is that if you want to seriously treat the spontaneous symmetry breaking mechanism that involves situations where fields are put on top of the potential, I'm just saying that there is no quantum mechanical description of that. There is no single fully quantum description of spontaneous symmetry breaking starting at the top, ending at the bottom of the potential. It's all semi-classical and all hand waving. And I'm quite surprised that such basic questions has not been addressed so far. And what I'm saying is that in order to address this question, you have to face the problem of negative square mass, which technically speaking equals the problem of tachyons in quantum field theory. So that's the physical motivation where we believe this is not just pure math, but actually there is a corner of existing reality that corresponds to those faster than light objects.
Interesting. Yeah. Thank you. Let's just check if there is any other question, like in the meantime. No? So yeah, let's thank Andrzej again.
Thank you very much.
Yeah, thank you.
Thanks.
Bye.
See you around.
See you.